Okay, let's dive right into this explainer. We're going to explore one of the absolute most mind-bending paradigm shifts in all of physics, the dual nature of matter and de Broglie waves. Seriously, if you feel pretty confident that you understand how solid objects work, well, get ready, because this concept is going to completely shift your perspective. And the crazy thing? This isn't just theoretical math, it's the fundamental reality of our universe. I want you to take a second and actually look at the physical objects around you. Look at the chair you're sitting in, the screen in front of you, or, even your own hands. We've all been taught to think of matter as solid, reliable, strictly physical stuff. But what if everything you know about matter is only half the story? Because, as we'll see today, we're about to completely shatter those everyday assumptions. It really all starts with this beautiful kind of scientific symmetry. So we already knew that light, which we've traditionally understood as a wave, can actually act like a physical particle in certain experiments. Well, the ultimate physics plot twist is the mirror image of that. Think about it. If a wave of light can act like a solid particle, then scientific symmetry dictates that solid matter should also act like a wave. Moving on to Section 1, the de Broglie hypothesis. Let's see how this radical idea builds into a formal scientific theory. The de Broglie hypothesis simply states that every moving particle has an associated wave nature. And what's really interesting here is the absolute totality of that statement. It means that literally everything that moves, no matter what it is, has a wave associated with it. Not just some particles, not just light. Every single moving thing inherently creates a wave-like behavior in the fabric of reality. So the crucial point is that we aren't just talking about abstract energy here. We're talking about particles with wave behaviors like electrons, protons, and whole atoms. The actual physical building blocks of matter itself. The very ingredients that stack together to make up you and me are fundamentally vibrating with a wave nature. It's just astonishing to realize that matter is deeply connected to wave behavior. Now for Section 2, the math of matter waves. Of course, a mind-bending concept like this needs a solid mathematical foundation, so let's unpack the mechanics. You might naturally be asking yourself, how do we even measure a matter wave? Like, if a flying baseball or a zooming electron genuinely has a wave, how on earth do scientists actually calculate the wavelength of a moving object? Well, here is the formula. Lambda equals h divided by p. Okay, let's dive into this beautiful, elegant little equation, because it literally changed how we understand the microscopic world. It's just three variables, but they completely redefine the dual nature of our universe. Let's quickly deconstruct those variables. What's really interesting is how this formula builds a bridge between two totally different worlds. On the left, we have lambda, which is the wavelength of the matter wave, the wave world. On the right, we have p, representing the momentum of the particle, the physical world. And connecting them on top is h, Planck's constant. That's an incredibly, almost unfathomably tiny number that dictates the scale of the quantum world. And this brilliantly illustrates an inverse relationship. Because momentum is on the bottom of that fraction, it actively fights against the wavelength. A larger momentum results in a drastically smaller wavelength. But on the flip side, smaller particles with very little momentum have clear, observable wave effects. It's a perfect cosmic balancing act. Which brings us to Section 3, why we don't notice. Let's build this into a very obvious reality check about our daily lives. I mean, if I am a wave, why don't I wiggle? It's a highly logical question. Since you technically have a moving wavelength right now, why don't you or the car you drive visibly jitter and diffract as you move through space? Why doesn't a thrown baseball blur into a wave pattern? The crucial point is revealed when comparing wavelength effects between macroscopic objects like cars and humans and microscopic objects like electrons. Because everyday objects have immense momentum compared to an electron, and Planck's constant is so unbelievably small, we're talking 33 zeros followed by a 6, our wavelength turns out to be infinitesimally tiny. It is completely unnoticeable and has absolutely zero physical impact on our everyday macroscopic world. So wave nature is significant only for tiny particles. This cleanly grounds us in the fact that while matter waves are universal truth, they really only show their visible effects in the microscopic realm. We don't notice it because we are just simply too massive. The wave nature is heavily suppressed by our immense scale, leaving these bizarre wave mechanics exclusively to the tiny particles of the universe. Let's move on to Section 4, proof and real-world impact. It's easy to think of this as just theoretical math, but let's look at how this directly shapes our modern technological world. We actually have real-life evidence for this. First, electron diffraction experiments definitively proved that electrons scatter and interact exactly like waves of water in a pond. But the second step is where the magic happens. We literally harness this wave-like behavior to power incredible tools like electron microscopes. By substituting light waves with electron waves, we bypass the limits of regular light and actually use the wave nature of matter to see the invisible. How cool is that? And why it matters goes even deeper. This brilliantly illustrates the monumental legacy of de Broglie's idea. It serves as the very basis for quantum mechanics, the famous Schrödinger wave equation, and modern microscopic imaging. Without understanding matter waves, our entire modern grasp of physics just completely falls apart. It is quite literally the blueprint for exploring the quantum realm. So, the crucial point to take away from this explainer is this beautifully simple one-line summary of our universe's dual nature. Every moving particle has a wave nature, with a wavelength inversely proportional to its momentum. That single sentence bridges the gap between the solid stuff we hold every day and the vibrating waves of the quantum world. I'll leave you with this final thought to ponder the next time you touch something you think is completely solid. If the tiny particles making up your body act as waves, how solid is the reality you perceive? The atoms in your fingertips and the table you're touching right now are deeply intertwined with this wave-like nature. What feels perfectly solid is actually a bustling quantum dance of matter waves. So, really, how solid is your reality?